so since I saw there's a Jello join the talk, then I will switch to the I will speak in English. So today I would like to talk about my recent topic, so published in Nature Communication. By the way, so can all the people hear me and also see my monitor as well as my pointer?
Yes, it's all okay. Yes. Thank you.
Okay, then I will continue. So, and first of all, I would like to thank the organizer. And okay, so then I think I can start. So today, my name is Huan-Yu Ku. I'm from the ICOKI, Institute of Quantum Optics and Quantum Information, and also the Department of Physics in University of Vienna. So today I would like to talk about how to classification of quantum steerability under the concept of the local filtering, and also I would like to introduce the relationship of the local filtering and the measurement incompatibility in terms of the quantum stability. So basically, from the title, you can see that in this talk, I will split this talk into two parts. The first part is how to classification of quantum stability, and the second part is how to use the local filtering and the relation between these two. And the second part is that how to find out the local filtering by the measurement incompatibility. So this is my outline. First, I will talk about some basic concept of quantum resource, including the entanglement, quantum stability, and the measurement incompatibility. And then follow the title. I will talk about how to transfer the quantum stability in a class under this local filtering operation. And then I will talk about how to find out the local filtering with the measurement incompatibility. Okay, first of all, we know that we said a state is entangled if it cannot express it as a separable form. So this is the basic concept, the most fundamental concept in the quantum mechanics. And we all know that the entanglement state is a useful resource. For instance, it can be applied on the quantum teleportation, in which you would like to transfer this state. So let me say this is Alice and this is Bob. So Alice and Bob are spatially separated. So we have this state. We want to transmit this state to from Alice side to Bob's side immediately. So the trick we can use is using the entangled state. So if Alice and Bob they share the entangled state, and if Alice perform a Bayer state measurement, then this is some certain way such that this state can be perfectly transferred to this location immediately. And we can use the so-called fidelity to test how close this state and this state are. So if rho AB is the maximally entangled state, then the fidelity between these two states will give you 1. So in this sense, we can say in this situation, it is a perfect quantum teleportation. And it has already been known that for the separable state, the fidelity must less than this value. So this D is the local dimension, local Hilbert space of this state rho AB. And there are some experiments. I will not show you the experimental setup because I'm a theoretical physicist, not doing the experiment. So there are 2 papers by University of Vienna and ICOKI. So they try to teleport a state from this side of Donald River to the other side. However, in this experiment, the best fidelity they observed would be 0.9. So in this sense, the entangled state sharing with this 2 sides is not maximally entangled. Okay, so there's a nature question, that is, can we increase the fidelity if the initial state is not a maximally entangled state? So what we can use is we plug in this so-called local filtering operation over here. Then there's some certain probability you can enhance your fidelity. So there's a work proposed by so there's one of the authors of this paper is also in this talk, so Jello. So if I explain it in the wrong way, maybe he can properly explain it. But okay, anyway, so the basic concept is that you have a initial state rho AB, and then you will apply the local filtering operation. So local filtering operation is a complete positive trace non-increasing map. So therefore, it is not a standard quantum operation we will use in the quantum information science. So in the standard quantum information science, we will always use the unitary operation or the complete positive trace preserving map. But here, so this local filtering, we sometimes will say this is the most general quantum operation. And the requirement it will, they satisfy is the complete positive trace non-increasing. So if we write down the local filtering in the class operator form, then you can basically express the state transformation in this formula. So this N denotes the success probability of this transformation. So if this A and B is CPTP, then N is equal to 1. We also call it the deterministic transformation. But here, the trick we use, again, I want to emphasize again, the trick we use is that instead of using a CPTP map, we use the CP trace non-increasing map, such that the state rho AB can be better. So this is the experimental result. So you can see that the red line over here denotes the fidelity before the local filtering, and the line over here denotes the fidelity after the local filtering. So you can see there's a advantage of applying this local filtering operation. So there's another concept called the Bayer non-locality. That is, if you have a state rho AB sharing with again Alice and Bob, and Alice and Bob they perform some bare box measurement in the sense that you don't need to fully characterize what the measurement are. But there's some input X and Y of this both bare box device and the outcome A and B. So in this kind of setup, the physical quantity you can access is the probability distribution, PABSY. So quantum mechanically, you can express as this form. And it has already been shown that for some entangled state, there is a function such that this formula can greater than alpha. And we call this alpha a local bound. And this formula is also called the Bayes inequality. Okay, and the violation value of the Bayer inequality somehow imply the two things. The first, the two applications on quantum information science. The first thing is the device-independent quantum key distribution, and the other is the device-independent random number generator. So as you see here, I emphasize the violation value over here. So therefore, again, the natural question arises: can we increase the violation value if we allow the so-called local filtering operation? So there's a paper published in Nature. They indeed plug in this local filtering in their experimental setup. And in the right-hand side, they say, in the left-hand side, so this is the density matrix of the state rho AB before the local filtering. And this is the state rho AB plan after the local filtering. So basically, you can see that in this matrix representation. So this state is very close to the maximally entangled state, and so therefore it can increase the violation value of the Bayer inequality. Okay, so basically this is our motivation. So we have the case in the entanglement theory. If we plug in this local filtering, then the entanglement can increase. And we also have an example on the Bayer inequality, which is if you plug in the local filtering, then the Bayer violation can increase too. So therefore, our motivation is, can we increase the quantum steerability with local filtering operation? Then in the next session, I will start to introduce the concept of quantum steerability. But currently, is there any question about what is the local filtering operation? And do I explain my motivation clearly?
Yeah, it's clear.
Okay, then.
I have a question. No?
Okay, please.
So, I kind of forget, when we apply this local filtering, we will prepare many pair of low AB and apply local filtering to obtain a higher entanglement state, low AB prime. And then so we were doing this many times. So we will have many of raw AB prompt and use it to do the teleportation or do the bell test? Is it like that?
Hello. Hello. Okay. Okay. So yeah, I heard your question, so I can apply to you. So the concept of the local filtering is not the same as the standard distillation on the quantum system. So in the standard approach, we will have many copy of a state and then you apply a global operation or some, some global operation on the sharing state. Then you can have a valid, you can have have a final state to be your target state, something like that. For instance, if you have lots of the mixed entangled state and you have many copy of the mixed entangled state, and then you apply some joint operation on that, and finally you can give you a perfect maximal entangled state, something like that. But here the concept of local filtering is that instead of many copy of this raw AB, we only have one copy, and then we send so the one of the party A to Alice and the other to Bob. And there's a local filtering operation. It can probabilistically distill the contents, the entanglement, in the sense that you can consider this is a mirror, and it will flat your photon into this direction and this direction. And if the photon pass through the in this direction, then we will say this row AB successfully. So this local filtering successfully distill the quantum state. And if the photon go to this direction, we said this local filtering fail. So therefore we have to redo the experiment. So do I answer your question? So basically you can see this from this formula. There's no copy. Yeah, there's no uncopy. Or you can consider this one-shot distillation protocol.
Okay, thank you.
I think it will be more easier to understand.
Mm-hmm.
Okay, if there's no question, then I will continue.
Sorry, from your explanation earlier,
Mm-hmm.
you mean the filter is just to fill out some unwanted low entangled state and just preserve the high entangled state. So it's like just like a filter. Oh, okay, it's a normal filter, right?
Yeah. Basically, this concept is the local, the standard filtering in the classical physics, in the classical world.
Okay, thank you.
Yeah, so you can imagine, when you want to make a tea, and when you put everything into the filter, then the tea will, live inside the filter, and the drink itself will you can have a pure drink water or pure drink tea. So this part is the thing you don't want. So then you just throw it away, something like that. Okay, then if there's no problem, then I can start. So basically the concept of quantum steerability is the mixture between the entanglement theory and the bare non-locality. So if there's a state row AB sharing with Alice and Bob, and here this is Alice and this is Bob, and also Alice performs some black box measurement with input as outcome A, and Bob, we assume that Bob always performs the quantum state homography. So therefore, the physical quantity Alice can have is the probability distribution PAX. However, on Bob's side, the physical quantity Bob can access is a set of quantum state rho AX. So let me give a concrete example over here. If Alice and Bob share the maximal entangled state in this formula, and we say that if Alice performs a measurement on the z-axis, if Alice's outcome is 1, then following this rule, we immediately know that the Bob state will be 0. So therefore, we can immediately write down the state Bob hold is 0 state. Similarly, if Alice performs a measurement on the x direction, if the outcome is plus, and following this state, then we immediately know that the Bob state will be, for instance, L state. So the Schrödinger say that the ability of remotely changing the quantum state is EPR stability. Okay, again, as I mentioned, the physical quantity we can access for Alice is a probability distribution, and for Bob is a set of quantum state. So therefore, we combine these two together and define a physical quantity called the ensemble, which is basically the probability PAS times the state rho AX. Again, let me use the same example to show you some concrete example. So as I mentioned, if Alice measure on Z basis with outcome 1, then Bob's state will be 0. So you just need to put this 0 and the outcome 1 into here. Sorry, there's a typo. It should be 1 over here. Then the Alice probability will be 0.5 in this kind of example. So then you can construct a one element in this ensemble. So I will not repeat the rest, and I believe you can sort it out by yourself. Okay, then we can have to also define what is the classical resource in the quantum stability, and we call it the local hidden state model. So the concept is that instead of sharing the entangled state, Alice and Bob, they have a set of pre-existing quantum state, and the ensemble is just a data processing of this set of quantum state row lambda. So I will use this picture to properly explain it. So if this lambda is equal to 1 to 4, and we denote a state A, B, C, D over here, then what Bob hold is that according to different kind of strategy. For instance, if we choose the strategy 1, then Bob can obtain the state A and D. And if you choose the strategy 2, then Bob will obtain the state C and B, so forth and so on. So finally, the final statistics will also give you a set of state, sigma AX, but you can see that this sigma AX is basically constructed by this 4 pre-existing state. Then we said this kind of model is a local hidden state model. Okay, and here I just write down the quantum realization of the ensemble. So this AAX is the set of measurement Alice performed, and this rho AB is the state sharing with Alice and Bob. And here Bob, he just doing nothing, and finally just trace out the A, the Hilbert space of A. Then you can obtain this ensemble. And also there's a concrete example. If we consider the state rho AB in this formula, and Alice always perform the measurement on the posy X and Z axis, then this is the final ensemble you will have. And following this kind of structure, then if there's a V, there is a value V of here, is V greater than 0.6, then your state is still can be steered. And if the visibility is less than this value, then there's no stability of this quantum state. So you can see that basically this the measurement Alice performed and this state ensemble, they looks very similar. So therefore, it can help us to introduce the concept of the measurement incompatibility. So here, this is a state ensemble. It's basically a set of subnormalized quantum state, and its classical model can be you can use the local hidden state model to describe it. And the next question is that is there a similar structure for a set of a measurement?
Could you go back to the next slide? I just maybe a bit too quick for me. Like usually, Y is like visibility equal to larger than 0.6 is steerable. Because I'm not familiar with this. So I know when I doing this to in a fail test or something, the visibility is if it is 1 is local and is smaller than 1 is non-local. So I just couldn't transform quickly to know why.
I think the visibility you mentioned here is different with the thing I'm seeing here. Since the visibility I mentioned is the classical the weight of the classical mixture of the mathematic intensive state and the mathematic mixed state. So the visibility I mentioned is this value V over here.
Okay.
So you can see that if this V is 1, let's say it's the maximally entangled state. And if this V is 0, let's say it's the maximally mixed state. So in this sense, you know, the stability should be, there should be a boundary, there should be a stability and a stability boundary between no, of this state.
Okay.
So basically, this plot is trying to tell you the strength of the classical and quantum world of this state.
Okay. Thanks.
Okay, so then I will continue. So the question is that is there a similar structure for the measurement incompatibility? So the answer is yes. The classical model of a set of measurement, we can use the joint measurable model to describe it. So the concept is that instead of using many different measurement, so since there's an index x, so each number of x denote the different basis of the measurement. Internet. Can you hear me? Sorry.
Yes, we can hear you.
Okay. Yeah. Sorry. Yes, the internet on my institute is very, very bad. I don't know the reason. Anyway, okay. So the natural question is that is there a similar structure for the measurement? And the answer is yes. We can use a joint measurable model to describe the classical set of measurement. So the concept of the joint measurable model is that instead of using a set of measurement, there's actually only one measurement devices. So you can see there's no button over here. So in this sense that you only have a measurement, a set of, okay, you only have one measurement, and this measurement will give you the outcome lambda, and you finally just do some data processing, and then you can simulate this a set of measurements. Okay, and if your measurement can be expressed as this formula, then we said your measurement is jointly measurable, otherwise it is incompatible. Okay, so there's a quick summary. So in the set of subnormalized state, we can use the local hidden state model as its classical model. And for a set of measurement operators, we can use a joint measurable model to describe, the classical function of this set of operation. Okay, so since basically you can see that these two models are very similar. So is there any further intuition between the quantum stability and a set of measurement operator? And the answer is that we can use the concept of the steering equivalent observable to transfer the problem on the stability into the measurement incompatibility. So here again, this is the setup for the quantum stability. Alice and Bart share the quantum state rho AB, and Alice performs some black box measurement with input S and outcome A. And on Bob's side, he always performs the state tomography, and finally he can obtain this rho AX. So in this setup, finally you can obtain is a state ensemble sigma AX, and we know that we can immediately know that the marginal state on Bob's side is rho B. So this rho B can be easily accessed by just trace out Alice part. Then you can transfer the problem from stability to the measurement incompatibility with this formula. Okay, and there's a paper. They show that if the state assemblage, so the problem in the quantum stability, is unstable, if and only if there's a set of measurement BAS is jointly measurable. So therefore, you can characterize the quantum stability with the measurement incompatibility, and vice versa. If I give you a measurement incompatibility, then you can know that there must exist some quantum stability problem, and they are basically equivalent. Okay, so let me give you some example. So the example I write is the Q2QP Warner state. So this is the state we consider. So this is the maximally entangled state with some visibility P. And okay, and again, if I consider this A, the measurement are the eigenstates of the Poti operators, then you can express your state assemblage in this formula. Then it's SEO, you can use this formula to transfer it, and then the result will be in this formula. And okay, and then if you compute the threshold of the steerability and the measurement incompatibility for these two quantum objects, the visibility will give you the visibility are the set. So it is equal to 1/√3. Okay, so now we can go back to the main idea. That is, we want to increase the quantum stability with the local filtering. So here, I want to mention one thing, that is we want our transformation is under the result theory. And in the entanglement theory, the valid free operation under entanglement theory is a local operation shared with classical communication. And again, as I mentioned again, if we allow the transformation to be probabilistically, then you can express everything in this formula, and this A and B are just a local filtering operation. And it has already been shown that for the two Q3 entangled state, there's two different class of this kind of the two Q3 entangled state. One is the W class and the other is JZ class. So basically what we want to do is similar. We want to define the valid transformation of quantum stability. And then if we construct a valid transformation, then can we classify the quantum stability? And then what is the valid operation of the quantum stability? Is the one-way. The answer is the one-way local operation with classical communication. So the concept is that you perform some quantum operation on your processing. So basically, this part is Bob will do this part. And hello, is my internet okay?
Yes.
Okay. And this is post-processing. So here we only consider the quantum operation, and you can basically imagine that what Alice do is just doing nothing. Yeah, she just do some delta function. And so therefore, this is the final assemblage you can obtain. So this is your initial assemblage, and then you apply some local operation. You apply some local filtering on this set of a state assemblage, and finally there's some success probability. And the success probability can be expressed as this formula. So it is the Bob's marginal, and if you apply the local filtering on Bob's marginal. And then I would like to introduce the two measures to characterize the quantum stability and the measurement incompatibility. I mentioned these two measures because it will be used later on. So the first one is the steering robustness. The concept is that it gives you an assemblage sigma AS, and you added some noise. So we denote the noise as tau AX. And finally, the assemblage is belong to classical. And it has already been shown that, mathematically you can formulate it as this formula. And this function is non-increasing under the one-way LOCC. So yeah, so this steering robustness will satisfy this relation. And the best thing of considering robustness best measure is that you can basically always transfer the problem of this form. And I only show the semi-definite program over here, and I will use it later. I also consider the so-called incompatibility measure, also in terms of robustness, and the concept is the same, giving you a set of measurement assemblage, and we added some noise, such that the total assemblage belong to classical model. And so again, basically all robustness measure can be expressed as a semi-definite program. So therefore we can compute the value of the minima t with the classical computer efficiently. Okay, so here are some summary between the steering and the measurement incompatibility. So the steerability problem of the state assemblage sigma AX, you can always transfer it into the joint measurability problem by this transformation. And the value transformation for local quantum steerability under local filtering operation can be expressed as this formula. And then we will use the steering robustness and the measurement, the incompatibility robustness to quantify the stability and the measurement incompatibility. So now I basically finished my background introduction. So now I would like to introduce the result we have. The first one is that we define the concept of the SEO equivalent class. So basically, the idea is that I give you two state assemblage, and then we compute its SEO. And if their SEO satisfy this relation, so that is okay. Basically, you can consider their SEO are equivalent, are the same. Then we said these two assemblage belongs to the same class, and the class is called the SEO class. And the other class we defined is the transportable equivalent class. That is, if I give you an assemblage 1, state assemblage 1, and then we can apply some local filtering operation. If it can be transferred to 2, and 2 can be transferred to 1 via local filtering operation, then we said they are in a transferable class. So now this is our result. So our result is that we find out that basically these two classes are the same. In the sense that I give you a state assemblage sigma 1 and state assemblage sigma 2, we can immediately compute their SEO. And we discover that if their SEO are equivalent, then we immediately know that these two state assemblage can be transferred with each other with local filtering operation. And we can define our local filtering operation basically with this formula. So basically the concept is that okay, maybe I can go back to here. So basically the concept is that you have this B equal to this B1 equal to this B2, and then you just plug in some reduced state row B1 and row B2, and then you finish your transformation. So this is this formula can be completely obtained by this formula. Okay, and the second result we have is that since this is a class, since we have an SEO class, in this class there's contains a lot of the state assemblage, and then we want to characterize the maxima and the minima state assemblage in this class. So we find out that the maximum assemblage we can have in terms of steering robustness measure is completely equal to the incompatibility robustness of the SEO B. And the minima stability in this class is equal to 0, or asymptotically equal to 0. I would say that asymptotic equal to 0 because here we use the infima instead of the minima. Okay, so in this sense, so this theory, combine this theory 2 and this theory 1 tell us that in the SEO class, you can always transfer an assemblage with a very, very low stability to its maxima 1. Its maxima 1 is equal to IR of B. But if you want to do this kind of transformation, then your success probability is very, very low. But you have the chance to do this kind of transformation. Okay, and here we have the suprema, and we discuss the other question is that whether this suprema can always access. And the problem is yes. If we compare the feasible, if we compare the dual SDP of the steering robustness and the measurement incompatibility robustness. So basically you can see that it looks in a very, very similar way. And the interesting thing is that, so this eta is a quantum state because it has to satisfy this trace eta equal to 1. And since this eta is a valid quantum state, if we take this eta as our rho B, then we finish the trend. Then this eta will give you will give us the optimal assemblage in a SEO class. Okay, so here again, I will give you some concrete example. If we consider our initial state in this pure state formula, and the rho B can be expressed as this form. You can immediately see this formula by tracing out the edits. And we said edits perform the measurement on pole X and pole Z, and then we can obtain our initial state assemblage look like this form. And if we compute its SEO, then the SEO in this example is coincidence equal to X and Z. Okay, and then our target assemblage, that is the reduced state, if this rho B can be expressed as this formula. And how we obtain this this formula is by using the feasible solution of the DSDP over here. So basically this eta over here is in this formula under this example. And since their SEO are the same, so we can immediately write down as this formula. So this is your given assemblage with the initial rho B. And this is our target assemblage and with the rho B part over here. So you can see that this one is equal to this one. And the only missing part is this sigma tar, right? Because I have already shown this sigma in over here, and rho B in is in here, and this rho B tar is from the STP. So this is the only remaining thing. So you can do the simple calculation, then you can obtain this is your target sigma tar, sigma AX tar. Okay, so therefore we can define the transformation of the Claus operator in this formula by solving this equality. And there's a concrete experiment. So here, Alice and Bob share the entangled state with some angle alpha, and they can, if Bob inserts some local filtering over here, so you can see there's a K0 and there's a K1, and if the result is K1, then they just throw away the experiment, and if the result is K0, then the experiment continues. So this is the result. So you can see that so the y-axis is the steering robustness, and the x-axis they call it the population imbalance, but basically it is the value alpha over here. So you can see that before the filtering operation, the steerability will decrease when this alpha increase. However, if we allow to insert in the local filtering operation, then the steering robustness is always give you the same value. So it is because in this example, after the local filtering operation, your final assemblage will always express as this formula, in the sense that there's no parameter alpha and beta over here. So therefore this plot is flat. Okay, and we also do the Q-tree example. Since in our model, we don't have any system dimension assumption. So therefore, we do the example on the Q-tree system. If we consider our initial state in this formula, so basically this is the pure entangled state. And we assume that this I is from 0 to 2. Then this state is the Q-tree entangled state. And we said that as this measurement is the two mutually unbiased spaces in the dimension 3. Then this is the steering robustness before the local filtering operation. So you can see that different parameter mu1, mu2. So each parameter mu1, mu2 will determine your pure entangled state. So you can see that the maximum stability occurred when the mu1 equal to mu2. Okay, And after we apply the local filtering operation, we observe that in this plot, all the steering robustness will equal to 0.2679. So in this sense, that you can basically imagine that all the state ensembles in this part are corresponding to the same class, and the stability of the that class is equal to 0.2679. Okay, here I have a very short conclusion about the result in the nature count. So here we completely classify the bipartite steerability by the concept of the SEO. And then we try to determine the transformation between the two ensembles by the local filtering operation. And also in this work, we try to solve the problem of the optimal bipartite content state and the measurement incompatibility. Okay. And so this work is collaborated with the Professor Xunliang Chen in Zhongxin University and Professor Yuan Chen in Chengkong University, and also my boss in University of Vienna, the Castina Bujoni, and also the Xie Zhongyun. Now he is a postdoc in University of Bristol. And there's some nature extension of our work we are trying to finish, and I will try to explain it. And instead of considering the random robustness, if we now in particular consider the concept of random robustness and the free resource robustness, can we also do this kind of transformation trick? And the answer is yes. So the first of all, I will have to introduce the concept of the random robustness and the free resource robustness. So basically it is we have the noisy part over here. And instead of considering arbitrary noise, if we allow some restriction on the noise itself, then we can define a different type of robustness measure. For instance, if we say this MAX and this tau AS are proportional to identity, then the robustness will go to the so-called random robustness. And if we say this MAS must be in the joint measure model, or this tau AS must be the local hidden state model, and then we set the robustness is free resource robustness. And we show that basically for these two different type of robustness, we also have the same result in the sense that in a class, so this B is the SEO class. So in a class of in the SEO class, the maximum stability in this class, in terms of the random robustness measure, will give you is also equal to the incompatibility, random incompatibility robustness. And the similar thing will happen if we consider the robustness measure is a joint measurable model, joint measurable robustness. And how we solve this relation is again basically compare the dual program of the semi-definite program. And there's also another type of measure called the weight-based measure. So the concept is that in if I give you a given measurement set, and there's a convex mixture of it, okay, if we allow this given BAS as a convex mixture of MAS and MAS-JN, so JN denote the model, the joint measurable model. And then we want to find out the maxima T over here. And we also find out that for this kind of the weight-based measurement, we also have this kind of relation. In the sense that the maxima stability in a class in terms of a weight-based measurement is also equal to the incompatible weight. Okay, therefore these two main, so therefore we basically finish the two main type of the measure of steering and the measurement incompatibility. And we show that they have the equivalent relation. And there's some further work we are investigating. That is, can we always using the quantum stability to quantify the measurement incompatibility? Since in the previous cases we consider are in terms of the weight-based and the robustness-based measure. So our question is that if I give you arbitrary steering measure S over here, can we always define the incompatibility measure as this formula? So in this sense, we want to show that whether this formula is the incompatibility monotone. And so currently this work is cooperated with the Castina Bujan and the Dr. Xie Zhongyun, and the work is still continue. But I just want to give you some further extension of my work. So basically, I think I finished.
Could you addressing a little bit more about, so like I have a assembly sigma and there's a SEO steering equivalence observable. Then like assemblage I know, but what is this observable? Like what it acting on what system? What?
Okay.
Yeah. Yes.
I think I can go back to this slide. Okay. So here, okay. So first, the steerability, the stay on some page is constituted by this figure, right? We have a row AB, Alice performs some measurement, and Bob performs the measurement, perform the quantum state tomography. And we have Alice, so Alice can perform a set of measurement. We denoted it by A. So this measurement A is in the Alice Hilbert space.
Okay.
But this steering equivalent observable is the transformation of sigma to B. But this B is not a real measurement in this experimental setup. So this B is just a representative incompatible question in terms of this experimental setup.
But
so
because
this is.
I just wonder. So, okay. So like 1x in Alice, like one measurement in Alice side. So it will corresponding to like a different B. So it's these two.
No. Okay. So there's no direct relation between A and B. So A is the measurement, Alice's measurement. So this is the real measurement implemented in the experiment.
Okay.
This B is a representative question in this experiment, this whole experiment.
Okay.
You can basically imagine that we can transfer this experiment into a question we denoted as B. And this B is a valid black box setup. Okay, I think I can explain it in a more easy way. So we have this figure, right? So this is, you can imagine it's a very complicated setup because you have a row AB, you have AAS, and you have row AS is very complicated. And we transfer this figure into a black box. So basically you can imagine there's a copy of this box from here to here. There's the box with input X and outcome A. And we denote this box as BAS.
Okay.
So this BAX is completely the same as the steering question in this complicated device, complicated experimental setup.
Is it like quantum channel can be think about like stay like the Choi Yamasaki? Something like it's similar. Like I transfer my channel to a state something.
Yes, you are right. Well, I transfer this complicated experimental setup into a single black box. Okay, into a black box measurement. Yes.
Okay, thank you.
I want to ask a question about the subnormalized state. Why the subnormal? What's the relation in subnormal, the factor over there? Because are they related to some filter percentage or why?
No, okay. So here we say this subnormalized state because we construct an ensemble in this form. So here this rho AS is a set of quantum state. So therefore the trace of this rho AS is equal to 1. And if we do the trace of this sigma AX, then this will give you 1, right? Because it's a very constant state.
Yes.
If you then, so therefore the trace of sigma AS is equal to PAX.
Yes.
Then this ensemble is not normalized. But it can be normalized if you divided this sigma AS with PAS, right? So therefore we said this sigma S is subnormalized state.
So this is determined by the Alice side,
Yes. So this P is the probability distribution Alice have.
Okay. Then where does the filter come in the whole setting?
Okay, so so basically you just plug in as I mentioned in here. So this is the local filtering we consider, and if the Bob can perform the local filtering operation. So go back to this figure, you can imagine the local filtering can be plugged in here. Before Bob perform the state tomography, the step pass through the local filtering operation first, and then Bob perform the state tomography.
So you mean the edit size already determined, the
yes.
subnormal factor is already there, and you just try to plug the filter at the Bob side before you do the tomography.
Yes. So here, as I said, we have already assumed that Alice post-processing is doing nothing. Yeah, but Alice just performs some delta function on her side, and Bob can plug in the local filtering operation.
Why you say it's post-process? Because you do the Bob side first, and then Alice later, or what's the sequence? What's the order?
I think they are in parallel because in Alice and Bob they are spatially separated, so there's no direct relation. I mean, there's no time. There's no concept of time in this experimental setup.
Okay, so they just do measurement or filter separately. Yeah.
No. So okay, Bob will perform the local filtering first. Then
Okay.
Bob will perform the quantum state tomography. But if you're saying whether there's a time sequence between Alice and Bob, I would say no.
Okay. I see. Then I'm also wondering what's the filter? I mean, it's only do you determine any filter percentage for the filter, or is there any parameter there?
No. In our results, all the filters are deterministic.
I mean,
okay.
50%, 50%.
No, so what? Sorry, what is the concept you are saying? I mean, what is the percentage of the filtering operation?
I mean, you filter out the unentangled part, and how do you determine the percentage of filter, or you just okay, you just filter out the unentangled state, so there is no percentage issue there.
Yes. As I mentioned, the basically concept is the filtering is that if it's success, then we continue the experiment. If it fail, then we draw it. We restart the experiment. So there's no. I don't think there's a concept for the percentage in this kind of local filtering concept.
And then what is the successful probability?
As I said, if the local filtering success, then okay, okay. Maybe I go back to here. Okay, as I mentioned, you can consider local filtering is the mirror, and if the photon can pass through the mirror, then it's success. Otherwise, it may flat your photon to this direction. And if the photon can pass, it's success. If the photon reflects, then it fail. So the success probability is that if you have the total count, which is the pass and reflect, you have the part. Okay, the total count is passed plus the reflection. And the success probability is the total divided by the part, the pass part.
I know, but that's from the experimental definition. I'm asking, can you predict the success probability?
Yeah, we can. Okay. Here. Okay. Okay. So as I mentioned, the main contribution of this result is this SEO equivalent class. So this is given, and this rho beta is from the SDP. So therefore, you can solve this sigma A as star, right? Because this is known. These three are known. These two are known. This is the only remaining thing we want to solve, and it is easy to solve, right?
Yes.
Okay. Then we want, and if you want to figure out the success probability, then you just need to find out. Okay. Sorry. There's a rho B in. There's a rho beta. So please remember these two reduced state. Then the success probability will completely equivalent to this formula. So this rho 1 is the rho in, and this rho 2 is the rho tar. So the success probability is the maximally eigenvalue of this equation.
Okay. So yeah, so this is your main result. I see.
One of our main results. So since this rho 1 is given, right?
Yes.
And this rho 2 can be solved by semi-definite program. And this unitary is not important, actually, over here. So everything is known, so you can easily solve its maximally eigenvalue.
Oh, yeah. Okay, great.
And it will give you the success probability.
I see. Okay, thank you. Yeah, it's very clear. Thank you.
I'm wondering, like, so in this slide, if like the sigma 1 and sigma 2 are SEO similar, then their like steering robustness will be the same.
No.
But
no.
Okay.
So okay. So our theory is that if I give you a sigma 1 and sigma 2, we can easily check whether they are in a SEO class.
Okay.
Because by this wait a moment, by this formula. So this formula is quite easy, right?
Okay.
So therefore you can have B1 and B2. Then you just see whether B1 is equal to B2. If B1 equal to B2, that means we know there's a local filtering can transfer this sigma 1 to sigma 2. And the question you are asking is that what is the, okay, you are asking whether the steerability of 1 is equal to steerability of 2, and the answer is not.
Yes.
So here, there's some concrete example. So if I give you an SEO, the maximum steerability in this SEO is equal to this value. However, the minimum stability in this SEO is equal to 0. But in this case, this sigma double prime and sigma prime, they are in the same class.
Okay,
Right.
so yes, so in the same case is in the sense they can be transferred to each other.
Yes. So okay.
So maybe
so
some
this theory two represent that this theory two hold. It must also requiring that this point I is satisfied.
Okay.
So you can consider it the sigma prime and sigma double prime, or they are in the SEO class.
Okay.
And we show that the sigma double prime can be very close to 0, and sigma prime can be equal to this value.
Mm-hmm.
So you can see the stability of sigma prime and sigma double prime are different.
Okay. Yeah, thanks.
Is there any further questions from the audience? If there is no further question, then thanks, Huan-Yu again.
Thank you.
Thank you.
Okay.
No，停止。